Hi there guys, well we've just done 3H, we're about to do 3I now, and the title for 3I says Polynomial Equations and Inequalities. Now frankly 3I is actually only about describing what polynomials are and discussing different cases for polynomials, for example quadratics, cubics, quartics, or linear functions for example. And so they come up with a definition for this, and then this goes on to talking about a division of polynomials as well. So we're going to look at a technique for a division of polynomials. Okay, so let's look at the definition to start off with that they give. So they talk about the polynomials are functions which map a real value, often x, to another real number, and we're just talking about mapping R to R. So you can see that this is not currently about complex numbers. This is just talking about polynomials. So polynomials are functions in this form. So they're saying that a polynomial with degree n would start off with a term of a lots of x to the n. So for example, that could be 3 lots of x to the 5. And that would be a quintic, that would be a polynomial of degree n or of order n. Okay, so it would start with this, and then you're going down. We could say, I don't know, we've got 4 lots of x to the 4 and minus 10 lots of x to the 3. But that would still be a polynomial of order 5 or of degree 5. Now, that's all this is really saying. That's just to unpack this kind of algebraic thing here. And we're ending up with a0, so we're just ending up with a constant term. Now, it could be that all of these a1, a0, all the way up to an minus 1, they could be 0, but with a polynomial of degree n, you'd have to have the first term being non-zero. Okay, so the a's are they your coefficients. They just say as well that if you want to talk about the degree of a polynomial, so if you want to say the degree of f of x, well, if we're talking about the degree of, say, for example, a quadratic, then you'd say that that would be 2 if f of x was defined to be a quadratic. Okay, right. So there we go. That's the definition. Now, after they do that, they do another little bit, which is a little bit odd. They say a linear combination of two functions can be expressed. Let's take this. Linear combination of two functions can be expressed in the form of a lots of f of x plus b lots of g of x. Now, I don't really see where they're going with this one really, because then they say, well, if you add together many functions, in fact n functions, then you could say, well, instead of using a and b and f and g, you could just say, well, we've got f1, f2, f3, all the way up to fn, and so using I as your subscript here and ai as your coefficient, with I being the subscript there as well. So I'm not really sure where they're going with that. And it's just to say, well, here is a definition that defines us adding together many functions, all of which are times by a. Now, more interestingly, next is they say, well, actually, in general, just take this one as well, right over it. So it's saying here that in general, you can say that polynomials are linear combinations of power functions. Now that's kind of interesting, because here are your power functions, and you could define f of x to be your power function. You could say this is x to the n or x to the I if you like. You could say, well, there you go, here's all our power functions. You could define that for I is between 0 and all the way up to, well, wherever you want to get to be honest, to say n. And then we could say our polynomial is now equal to the summation of all of our coefficients, if you like, a for I, so for each one of these which we go through, and then you're saying, well, then we've got f I of x. So we could say that, for example, for x squared, if we put I in as equal to 2, we have an associated a2. And then we could define this for I as 0, because remember, we can get x to the 0 as our constant term, all the way up to n, and that would define our polynomial. But we'd have to define our power functions in the first place, and that's this thing here. And they actually haven't done that in the book, but there you go. That's the kind of interesting thing for summation of your polynomials. Right, okay, whittering on a little bit here, so let's just push on a little bit. They talk about the zero polynomial, just saying, well, just for completeness, we're going to say that, sure, we've got a constant polynomial, which is just a straight line. Okay, it's the one which has x to the 0, c lots of x to the 0 gives us a constant term, and that's a constant polynomial. But the zero polynomial we're just defining to be equal to 0, which is also a straight line. And they talk about a little discussion here, is they're saying, well, listen, if the constant polynomial, okay, if we're saying that f of x is equal to c, is our constant polynomial, which is basically using a power of 0, then how on earth do you define this zero polynomial? Okay, how is that? What are you timesing that by? X to the power of what is c0, or is x to the power of -1, or x to the power of minus infinity? What's going on there? So this one is less clearly well defined, and they actually talk about the fact that this is not particularly defined in mathematics as well. There's still some discussion about this, but we still all agree that the zero polynomial is going to be equal to 0. Now, to be honest, most exam questions won't test you on that, and it's just not particularly interesting when it comes to questions in general. Okay, when we talk about linear polynomials, we're basically talking about linear functions, so f of x equals mx plus c. So there we go, we can see some linear polynomials there. And quadratics, pretty obvious. There we go, so we can get positive quadratics and negative quadratics. And that will change the shape, whether we get u's or n's. And they talk about things being concave upwards, positive quadratic, and concave downwards, being a negative quadratic. Now, we've dealt with that before. The shapes there which are created are called parabolas. Okay, now when we come to cubics, they discuss this one a little bit, and I'm just going to flick to Desmos. I'm going to say, well, here's your basic cubic, and you can put on some coordinate points there, 1, 1, and 2, 8. You can't see just at the moment, and of course on the other side you're getting -2, -8. So that's just cubing numbers basically. Let's zoom out a little bit, and there we go. We can see what we're getting there. Okay, so let's just zoom back in a bit, get rid of those, and they're discussing a little bit. They're saying, well, what happens when you then add on another term? Say, for example, you add on x cubed. What happens? Plus on x squared, right? So if we plus on x squared, let's zoom in a little bit here. Maybe let's put on a bigger amount of x squared. Let's say 3x squared. Let's say 2x squared. There we go. It's quite nice. So you can see that you're getting this shape. And what happens if you change that to a minus? There we go. It's shifting the whole thing there as well. So it's just being aware of some of the patterns. And in fact, if you're finding your roots to these, you'll see, for example, steal this one here. We've got this. Now, if we were going to sketch this one here, we could actually find our roots, and we could, by factorizing this, we could say, well, let's take x squared out of both of these, and we can see then we're getting x minus 2 as our factor. And so we can see we have a repeated root at x is equal to 0. We're getting that repeated root, and then we're getting a root out at x is equal to 2. So we could sketch this pretty quickly, in fact, because we can see we have this repeated root here. But really, we have x times x minus 2. So we've got x is 0 twice. That has to be a turning point there. That's where we're getting our repeated root. Okay. So again, if we look back at Desmos, what I forgot to say about y is equal to x cubed is that this one has a point of inflection and not too extremer. Okay, so this one just has this point of inflection. When we look at these graphs, we can see that this one goes like this, and it doesn't have a maximum turning point and a minimum turning point. So it just has this point of inflection here. Whereas the green graph, as soon as we start involving other terms, we then start getting maximum and minimum turning points, and we get our point of inflection still, which is going to be here, And we'll deal with that in more depth when we come to differentiation and second derivatives later on. Okay, well, just again to be aware of some things, again, we can put in, say, for example, minus 3x there. It's going to give us this shape. Okay, and again, that's going to be pretty easy to factorize and find each of those roots. And then we could put plus 3x here. What's going to happen when I put plus 3x? It's going to reflect. Oh, right, it looks, we zoom out, it looks a bit like the other cubic, in fact. So it's just making that cubic more extreme. It's adding on more positive values to the side when x is positive, and it's adding more negative values on to the side when x is negative. Okay, so there we go. I mean, we can play around with that. Obviously, if we put on constants at the end, if we put on a +2 there, shift the whole thing by 2. Okay, so those are cubics. That's just sort of general shapes for cubics. Oh, and one thing I've forgotten to do there is if I put a minus x cubed on, I'm going to flick it around the other way. So all of our negative heights are now going to become positive. Okay, well, we've done work on functions before, so let's not labor this. A little investigation here as well, which is basically what we've just talked about. And then they talk about a little bit here about just saying, well, look, these two graphs look quite different, but when you zoom out, they look quite similar. They follow similar patterns. And that's because the x cubed part is going to dominate when x is large or when x is very small. So when the magnitude of x is large. So x cubed, say, for example, when we put in x is 10, x cubed is 1,000. That totally dominates all of the other parts of the expression. Okay, they also talk about polynomials being continuous functions. That is, there's no break. There's no asymptotes. They are totally continuous as long as we've got just our a lots of x to the power of n and so on, all on our numerator, if you like. We're not talking about rational functions here. Okay, we're talking about just a simple polynomial function, all written on the numerator with a divided by 1, if you like. Okay, now it starts talking about the factor and remainder theorems, but they actually turn up in the next exercise. So I'm going to leave those to the next exercise. What they're really talking about to start off with is a division of polynomials. And here it says you need to remind yourself how to divide two numbers by long division. Maybe we should do that first. Okay, so let's just talk a little bit about long division. Okay, well, maybe let's do a long division with, say, for example, a division by 12. Okay, so let's say, I don't know, let's say 2,000 divided by 12. And it would be useful in long division to remember to know our times table that we're dividing by. So we've got 12, 24, 36, 48, 60, 72, 84. We were going after that 96, getting 108, and then 120. It's often useful if we're doing long division to have the times table written down by the side. This is 1 times 2 times 3 times 4 times 5, 6 times 7, 8, 9, and 10. Now, not everyone has done long division in previous courses. I'm aware of that. And most people have done short division. And of course, you can do this by short division. So that's saying 12 into 2 doesn't go, so carry the 2. And 12 into 20 goes once. And then we have a remainder of 8. And so that's your short division. But long division is for when the problem gets more complicated and the divisor becomes more complicated as well. And so in order to do this, we'll still say 12 into 2 doesn't go. Now 12 into 20 goes once. Now 1 times 12 is 12. We do 12 away from 20, which leaves us with 8. So that 8, where we would normally put that here as our remainder from doing 12 into 20 goes once, and our remainder is 8. We've now put it down here. So we're just making it clearer what our steps are. And then where we'd normally have 8 here, you'd have, that would be 12s into 80. Well, you're going to bring down that 0 here. So now we're saying 12s into 80. Well, 12s into 80 goes 6 times. It doesn't go 7 times. But 12s into 80 goes 6 times. Now 6 times 12 was 72. And then we're going to do that same process again. 72 away from 80 gives us 8 again. So that would normally give us 80 there. So now we're going to bring down the 0 here. Again, we've got 12s into 80 goes 6 times. And 6 times 12 gives us 72. And then our final remainder, just squeezing it at the bottom there, is 8. Now 12s can't go into 8 because 8 is now less than 12. Okay, so what we've got is our remainder 8. Okay, and the way in which we can write this as well is saying 2000 divided by 12 is equal to 166 plus, or rather, and 8 left over, which is yet to be divided by 12. Or you could even put that as plus 8 twelfths, which is kind of what we're going to do next, really, but with polynomials. Now, 8 twelfths can obviously be simplified, and that's fairly straightforward. But this is a technique of long division. Okay, so let's have a look at this question here. We've got example 1 and see how they do this. Okay, now you're going to need plenty of practice with this. And so this one is saying divide this by this thing here. Right, so we're going to do 3x to the 4 plus 4x cubed plus 2x squared plus 3x minus 1. It's a little bit like us saying, well, look, here's our units, here's our tens, here's our hundreds, and so on. And in fact, if x is equal to 10, in fact, that turns into a 5-digit number there. Okay, we're going to do our division, division, and we're going to divide by this polynomial, which again, if x was 10, this would be in the hundreds. So we've got x squared plus x minus 2. Now, we don't have to write down the times table for this now, but what we're going to do is say we're going to do this into this. Okay, well, x squared into 3x to the 4 is where we're going to start here. Right, so x squared into 3x to the 4 gives us x squared, and I'm going to put that in the x squared column, and 3 lots of x squared, in fact. Okay, so how many x squareds go into this? That's like saying, what's 3x to the 4 divided by x squared? Well, if we cancel this and this, will end up with x squared on the top, so we've got 3x squared. Okay, so now we're going to do 3x squared times by this thing here. So 3x squared times by this gives us back the 3x to the 4, which we're happy about. But it also gives us plus 3x cubed, so that's doing this times by this. Now when we do 3x squared times by minus 2, we'll end up getting minus 6x squared. Now, just like with long division, we're going to do a subtract here. So this and this leave us with nothing. When we subtract those two lines, 3x cubed away from 4x cubed leaves us with x cubed. And plus 2x squared take away minus 6x squared gives us plus 8x squared. Now we're going to do the same process again. Now I guess we could bring this down if we want to, the 3x. But in fact, we don't really need to here because we're only really saying what's x squared into this. Okay, so it's only this into the first term. Now, when we do our multiplication, we'll probably need to bring this down in a bit, but let's not worry about that just at the moment. So we're saying x squared into x cubed is going to give us x times. Okay, so that all we're doing is x cubed divided by x squared gives us x. And so x times by x squared gives us x cubed. X times by x gives us plus x squared. And x times by minus 2 gives us minus 2x. And there I see I've got a gap here, so I need to bring down my term here. So that becomes obvious when it's missing. So now again, we're going to do a subtraction of these two things. So this, take away this disappears. We've got x away from 8x squared x squared rather away from 8x squared leaves us with 7x squared, and minus 2 away from 3x gives us plus 5x. Okay, now last position that's available here, we're going to do x squared into 7x squared gives us 7 times. 7 times this thing at the front, so times by this, is going to give us 7x squared, which is what we wanted, and then plus 7x when we times by the x, and then minus 14 when we times these two terms. Now, of course, we've got to bring this down again. So that was missing. So we bring that down and then do a subtraction of these two. And we'll see we've got minus 2x there and plus 13 when we do the subtraction. So let's just review what we've got here. We've done a function of x divided by another function. So we did this function divided by this function. So I'm calling the original function f of x, and I'm calling our divisor g of x. And what we're left with is this thing up here. So that's called our quotient function. So that's the quotient of x. And then we've also got a remainder. So this is what's left over, plus our remainder, which is yet to be divided by g of x. And we can see that we can't do this into here because we no longer have an x squared in this function. So we can't say how many x squareds are into this, or rather we could, but then we go into x to the minus 1, and we don't go there. Okay, so this is essentially what we've just done. We can say f of x, this thing here, is divided by this thing here is equal to 3x squared plus x plus 7, and then plus our remainder, so plus this thing here, which is yet to be divided by g of x, which is yet to be divided by this. We can write that in another way if we want. We can say f of x is equal to the quotient of x times by our divisor plus r of x, plus our remainder. So all I've done there is times throughout by g of x, our divisor. Okay, and let's have a little look at seeing that we've got that one right. So they're saying the answer is 3x squared plus x plus 7. Okay, and they've written it in, okay, if you have a look at this one, they've actually written it in this format here. They've said f of x is equal to the quotient times by g of x plus r of x. So when it says use all steps in the long division of the two numbers to divide by your original function by x squared plus x minus 2, well, in fact, I would write my answer as, here's the division, there's the division. The division is my quotient plus my remainder, which is yet to be divided by the divisor, the second function. However, they've written it in this format here, and it's just an alternative format of this thing here. Okay, from my perspective, to answer the question here, to divide these two things, that's what we end up with. That's actually the answer. However, when we look at it, so we look back at what the book has done again, they've said, well, there's your f of x on the front, 3x to the 4 plus 4x cubed, and so on, is equal to, and then they've said that's equal to g of x times q of x, g of x being our divisor. They've just got it a different way around to me. I've got q of x and then g of x, same thing. And then plus the remainder, so plus the remainder on the end, I've got minus 2x plus 13. Let's just check, I've got minus 2x plus 13 as well. Okay, this one, we've got 3x squared plus x plus 7 and 3x squared plus x plus 7. Yeah, we got it right. Okay, now there's lots of areas for you to go wrong there, lots of particular steps which we go through to where you can go wrong. So you really do need a lot of practice with this one. What's kind of interesting is at the end they say stop when the degree of the remainder is smaller than the degree of the divisor. Let's look at this. We stopped when the degree of the remainder, so that's here, is smaller than the degree of the divisor. Okay, and in this theorem here, basically stating the same thing as I've stated there as well, but it also says underneath, it says the polynomial q is the quotient and the polynomial r is called the remainder. And it says, notice that the degree of g is greater than the degree of r. I think they mean the degree of q is greater than the degree of r there. No, they don't. G is the thing that we're dividing by. No, that's fine. Sorry, ignore me. Okay, yeah. The notice that the thing which we're dividing by has a degree which is greater than this thing here. Yeah, q of x is not what we divide by. G of x is what we're dividing by. Yeah, they're right. Okay, they're right. They're good. Okay, let's not doubt it. Okay, so there we go. We've got 3i, and I really suggest that you have lots of practice with this so that you get good at the process. And it is just a process here. Oh, one little extra thing. Okay, one little extra thing. This can be done differently. Okay, now have a look at this thing here. What we can do, extra, what we could do instead is we could say 3x to the 4 plus 4x cubed plus 2x squared plus 3x minus 1. Now, remember what we wrote. We wrote f of x is equal to, and let's just be consistent with what the book's saying. They're saying g of x there, so that's our divisor, and then times q of x plus r of x. Now, what you can do is take this f of x and set it equal to g of x, which is the divisor again, so this thing here. So this is an alternative method. If you don't like what we've just done there, it's another one which we could practice. Times by q of x. Now, q of x is our quotient, and we definitely need an x squared times an x squared to give us x to the 4. So we're going to set this up as ax squared plus bx plus c. And remember that the remainder always has a degree which is 1 less than the divisor. Okay, so the divisor is this thing here, so we just need to set up plus dx plus e as our remainder here. Okay, now since we have 5 terms here, since we have 5 unknowns, we should be able to set up 5 equations by comparing coefficients on both sides. So what we can do is multiply out all of the right-hand side here and simplify everything on the right-hand side. So get together all of your x to the power 4, factorize out your x to the power 3, factorize out your x to the power of 2, and so on. So you'll have all of your terms, and your coefficients will be in terms of constants and a's and b's and c's and so on. And then you can compare both sides. So for example, if we multiplied out this side, there's only one way, identity there, of getting out x to the power 4. So you can say ax to the power 4 plus blah, blah, blah. Okay, and we've got 3x on this side plus blah, blah. Now, we can see straight away that a has got to be equal to 3. That's by comparing the coefficients of x to the power 4 on both sides. Now, if we keep doing that, if we compare the coefficients of x cubed all the way down to x to the power 0, then we will be able to solve all of those equations and work out what a, b, c, d, and e are. Okay, so this is a different process of using this format here, which is equivalent to doing f of x divided by g of x. So use this format here, compare coefficients on both sides, and you will find out what your quotient is and what your remainder is as well. Okay, so a different approach, worth trying out as well. Okay, well, thanks for listening. Next time round, we go on to the factor theorem and the remainder theorem. Okay, see you later.